So I was asked to talk about Euclidean lattices in general. So I will give really an introduction to Euclidean lattices, and I made the choice of not talking so much about the computational aspects because, first of all, so I won't talk about the applications in cryptography, for instance, because first you have the talk by Ilya tomorrow, which is really related to cryptography and applications in cryptography. And also you can watch the Pacific talks, so the talks from the winter school, which is happening in the same days, and they are really oriented toward algorithms and computational aspects of lattices. So actually I decided to talk more about the geometric aspects and the algebraic aspects of lattices. So for instance, the motivation would be a little bit different. I will really focus on the standard problems related to lattices. Essentially, the main one I will consider will be sphere packings, and also related problems like covering and kissing number. So this will really be my point of view today. And also, as I told you, this will be an introduction. So I will really try to keep it slow and easy. So I really start from the very beginning, all the very first definitions. I don't assume anyone to be familiar with lattices, even if we heard of them like in the previous talk and also yesterday in the talk by Alex. But I really want to introduce the first definitions for you to understand what is a lattice and also what are the important properties of lattices. So if you find a lattice sometime, what are the invariants you can construct, you can compute, and what are also the objects related to a lattice. And also I want to present, to give an overview of, okay, what are the famous lattices. So you will see that main invariants, they are really hard to compute. But for some families of lattices, we know things because we know them well. They are really the standard lattices and they are famous. Some of them are really beautiful, and you will see that they are also powerful. So I want to tell you about these families of lattices that are well known. And I also want to tell you some information about how to construct nice lattices. So for instance, from coding theory or from algebraic number theory. And then in the end, I will go back to the motivation, and I will go back to the problem I will introduce right now, and I will tell you how lattices can help solving these problems and which kind of information they give about those problems. Okay. And by the way, feel free to stop me at any time. So I will make several breaks like after each part, and yeah, feel free to stop me if something is not clear or if you have any comment or remark, and I will be glad to if you stop me. Okay, so let's start with some motivations. So let's start with a concrete example. Okay, that's a stupid example. Just imagine that for any reason, this will never happen in reality, of course, but for some reason you want to keep people away from each other. So you want people you want to force a distance between people. So for instance, you want to force 1 meter distance between two persons in a public space. Okay, so and the question is, how do you deal with many people? So just imagine you have many people in a room and you want to place them in such a way that you keep 1 meter distance between every pair of people. So what is this problem? Actually, this problem, so you can just imagine to draw a circle around every people. So a circle of half a meter. And you want these circles not to overlap, because here, for instance, you have these 3 people, they are too close from each other because the circles here overlap. So this one is safe, for instance, and the other one, and those one are not safe. So what is this? If you forget about the person and you just think about the circles, you really want the circles not to overlap, and this is exactly what we call the sphere packing problem. So you have spheres or balls. You can think about both. That doesn't matter. You can think about both. And you want to organize them in the densest way. So you want to put as many people as possible, as many balls as possible, in such a way that they do not overlap. This is the sphere packing problem. So this is, of course, like a example, but you also have some. So this is in low dimension, for instance, dimension 2, 3. We see some obvious applications, but this is also useful in higher dimensions. And for instance, you have some motivations from coding theory and information theory. So for instance, if I consider, so I have a noisy channel over Rn. So I assume that the messages that I can send are special points in Rn. And I assume that with high probability, the message I will receive, So if X is sent, the message I will receive will stay in a ball of radius X, of center X and radius epsilon. So you have what you see will be in the ball of center at the message with radius epsilon. So what happens in reality? So for instance, here, just imagine that I know the possible code words. So that those are the xi's, x1, x2, x3, x4, and I receive y. Then what I can do, I can just draw the ball centered at y of radius epsilon. And here I have only one point here. So what does it mean? This means that the message that was sent was exactly x1. And I can decode and I know what was the message that I was sent. But the problem is if here I draw the same ball, but here I have two possible code words, then I'm confused here. I don't know whether it was x1 or x3 that was sent, and then I cannot decode. But what does it mean that here I have two points in the ball, two messages? This means that if I look at the ball centered at x1 and x3 of radius epsilon, they overlap. So once again, what do I want? I want these balls not to overlap. So So I want to find, and of course, I want to transmit as many messages as possible. So I want to have many points, many messages, so many spheres that are arranged in a dense way, in such a way that the sphere do not overlap. So this is for sphere packing. That's a very classical problem, very old also, but you will see that this is also very hard. Okay, so this is the first problem, and what we often called the dual problem of the packing problem will be the covering problem. And this also, you can understand also in a dual way. So now you want to make sure that people respect social distancing. So what do you do if you want to make sure that they respect it? You put some cameras. And so for instance, you can assume that one camera will cover a radius of any radius, a given radius. And you want to know how to arrange these cameras in such a way that you can control everyone. But of course, you want to save money, so you want to use as few cameras as possible. So you want to arrange your cameras in such a way that they really cover the space, but you don't have too much overlap. So this time you want them to overlap, but not too much, just what's needed. So that's the covering problem, which is the dual of the packing problem. And the last problem I want to consider, this will be the kissing number. So in this time, this is also a problem with spheres. So this time I fix a sphere, a unit sphere, for instance. You can rescale afterwards. This will be the blue one in the center. And then you want to know how many other unit spheres you can put around, touching the central sphere in such a way that the spheres around do not overlap. So here, this is the configuration. So the blue one is the central sphere, and around you have 6 spheres. So this means that here the kissing number in dimension 2 will be 6, because this is obviously optimal. You cannot do anything else. So this is also a problem with spheres, but this is a local packing problem. So the previous packing problem was really global in the Euclidean space, but here this is really local, like around one sphere. That's the local version of the sphere packing problem. And also you can see it a little bit different. So instead of looking at the centers of the spheres, you can look at the projection of the sphere on the sphere on the surface of the central ball. And then you want to know how many points you can put here, but they're not allowed to be too close. What does it mean to be too close? It means that the angle between them cannot be too small, right? So you want the angle between them to be at least pi/3. So this is again a packing problem, but here you are packing points on the sphere. Okay, so this will be the 3 problems you should keep in mind for today. And okay, I presented them with balls, and you can keep always balls in mind for this, but you can replace the Euclidean sphere by any other convex body. This is also something which is studied, but the main object to look at is really the Euclidean sphere. And they're all very hard. So I will tell you in the end about the results, but you will see that these are really long-standing problems. You have many applications of these problems, like in physics, in chemistry, for instance. Also, you have some relations with energy minimization of points. So these are really useful problems in reality, but are really, really hard. And so the question is, okay, how can you attack such problems? So for instance, we don't assume any structure on the point so far. So what can we do? We don't have any way to attack the problem. So the idea is, okay, what happens if I impose some algebraic structure to the set of points. Like for instance, if you think about the coding theory, you can call code which is just a set of points in the Hamming space. And then you have linear codes in which you impose these points to form a linear subspace. So then you impose some algebraic structure and you have more constraints, and it's easier to understand and to get some information on these structures. So here we want to do the same. So for these problems of sphere, we want to impose some structure, some algebraic structure. And what's the way of doing so? The way of doing so is to consider Euclidean lattices. So for the ones who are familiar with coding theory, Euclidean lattices are really the equivalent of linear codes for this situation. So that's why I will be interested in Euclidean lattices today. Okay, any questions so far before I start definitions? No question? Okay. I'm not seeing the chat, so if you're asking questions in the chat, you can unmute yourself and ask them.
No, there are no questions yet, but yeah, please continue. It is really interesting.
Okay. So as I told you, I will start very, very easily. So what's a lattice? So fix a basis of Rn or a subspace of Rn. So you take just a set of vectors that are linearly independent over R. And what will be a lattice? So a lattice will be all the linear combinations of these points, but with integer coefficients. Okay, so you take a basis of Rn, for instance. You can take a subspace, but yeah, we can just imagine this will be full rank. And you look at all the linear combinations with integer coefficients. So you get a grid, and you get a uniform distribution of points in the space. That's the way you have to think about it. So here I took the canonical basis of Rn, but you can take any other basis, and you will get any other lattice. For every basis, you get a lattice. Okay. And what's important here that it's a discrete subgroup of Rn. So you're really points that are uniformly distributed on the space, and you don't have any accumulation point. So that's why I ask the vectors to be linearly independent over R, and not over the integers. Because for instance, in R, if you take the subgroup generated by 1 and square root of 2, so they are linearly independent over Z, but then if you look at all the linear combinations, you will get accumulations at 0, for instance. I don't want this. I really want something discrete in R. Okay. So let's be a little bit more formal and not just geometric with picture, but let's write it down properly. So Euclidean lattices, so I need a Euclidean structure. So just think about Rn with the Euclidean scalar product so far. And the lattice will just be the Z module generated by a basis of Rn or In. So you just take E1, Em, linearly dependent over R, and you take the Z module generated by that. Then, of course, E1, Em, this will be called a basis of lambda, and the number of vector will be the rank. That's as you can imagine. If you want a generating matrix, then you take the matrix whose rows are the elements of the basis. So here, be careful. I'll be careful of myself because usually first I'm always dealing with full rank lattices, and I try to be more general here today. And also usually I'm used to work with column vectors, but I saw that in exercises you're using row vectors, so I try to stick with it. But there might be some mistake, and be careful with me. Okay, and then once you have a generating matrix, then how do you understand the lattice? The lattice will just be all the linear combinations with integer coefficients of the rows of the matrix. So you can write here in the more algebraic way the lattice. Okay. And now, okay, of course, for one lattice you get a basis, but you can have many bases. And how do you see that two bases span the same lattice? That's not hard to see that this will be the case if and only if you can go from one basis to the other one by multiplying by a matrix which is inversible over Z. So which means that the coefficients are integers, but also the coefficients of the inverse matrix are integers. This means in particular that the determinant of M here will be plus or minus 1. Okay, another matrix that will be important for lattices will be the Gram matrix, which is just the matrix made of scalar products. So at the position ij, you will have the scalar product between ei and ej elements of the basis. So this will be a square matrix, and you can compute it just by taking the product between the generative matrix and its transpose. And also something which is important is the determinant of this matrix, and this will be the determinant, what we call the determinant of the lattice. Okay, so this was for some definitions. Now let's go back to geometry. So now if you take the basis and you look at the polytope which is spanned by those vectors, you take the parallelepiped, then you get here this beautiful square. And actually you want to know the properties of this region. Actually, there is a very nice property that if you take this region and you translate it at any point of the lattice, then you get the tessellation of the space. You get cells, here squares, and you get a partition of the space into equivalent cells. And such a region, this is what we call a fundamental region of the lattice. So here this was with this nice basis, but if you take another basis, then you will get the same property. If you translate it at any point of the lattice, then you get the tessellation of the space with equivalent cells. Okay, and in particular, if you get this property, so whenever you have a fundamental region, what's important is that the volume will always be the same. And this volume, so this will be an invariant of the lattice, and this is what we call the volume of the lattice. So sometimes you call it also the covolume, because actually you're looking at the volume of the quotient of Rn by the lattice, but you can also call it the volume, and here I will call it the volume of the lattice. Okay, and if you want to compute the volume, then you just need to compute the square root of the determinant of the Gram matrix, which is the square root of the determinant of the lattice. And in the case your lattice is full rank, then you just need to compute the absolute value of the determinant of the generating matrix. Okay, so determinant, if you have a basis, you're able to compute it, and that's not hard. Okay, so here I showed you two different bases, and you might agree that there is one basis which is nice and the other one which is ugly, which is even more the case here. So if you look at these two bases, they span the same lattice, which is the easiest lattice, the lattice Zn. But you might agree, depending on the taste, that on the left-hand side, the basis is nice, and on the right-hand side, the basis is not so nice. So what does it mean to be nice? What does it mean to be not so nice? Nice means that I have a basis with short vectors and almost orthogonal vectors. So here in this case, I do have orthogonal vectors, but in general, there's no reason to be, and in general, there won't be. But still, you want vectors to be as close as being orthogonal as possible. So for instance, the basis on the right-hand side is terrible because the angle between the elements of the basis is awful, is almost flat. Okay, and if I give you a lattice with any basis, it is well known that computing a reduced basis, this is something which is really hard. And especially if you want to find the shortest vector, here I have a basis on the left with short vectors. And this is something which is known to be really hard. I won't go into details because I told you I won't go toward these algorithms, but this is known as NP-complete. This is very hard. And I guess, yeah, you will hear about it like in other talks. And of course, you know that we have the LL algorithm that allows you not to solve exactly this problem, but to solve this problem up to some approximation factor. And even if the first time you look at LL algorithm, you think that the approximation factor is not so good, like in practice, this is already efficient and you get very nice applications. For instance, if you have numbers, you don't know where they come from, then you can find some integer relations that are satisfied by numbers, or almost satisfies, and this can be really useful in practice, especially like if you're dealing with numerics or with floating points, then you can recover some exact numbers going from numerics. That's really important. But again, I don't want to go so much into LLL. You have exercises about LLL. If you've never seen about it, I recommend to do the exercises and yeah, that's very, very beautiful. Okay. So more definition, of course. So if I have a lattice of rank, and so now I assume it to be full rank because I don't want to make any mistake. What will be a sublattice? Of course, that will be another lattice that will be included in the first one. And if the other one is also full rank, then you have some relation into between the volumes. Basically, the quotient of the volume will be the inverse of the index of the subgroup. So here, so be careful because the big lattice lambda here is the one in blue, so with the blue circles, still Zn. So this will be the one with the small volume. So this one has volume 1, as you can see here, and the other one will have volume 3, and 3 is exactly the size of the quotient here. If you look at it, you have 3 circle points in the quotient. If you forget about the boundary, if you are careful with boundary. Okay, so if you have inclusion between lattices, the index will give you, if you know the volume of one of them, then the index will give you the volume of the other one. And some other important lattice, if you're given a lattice, it will be the dual lattice. What is the dual lattice? Then you take all the points in Rn, such that for every element of, such that the inner product with any element of your lattice will be an integer. So that's also really useful. And what you know also, you know that the volume of the dual will be the inverse of the volume of your lattice. Okay, so one more important object related to a lattice will be the Voronoi cell. So what's the Voronoi cell? So you fix 0, so let's just look at it 0, and I want to understand what are all the points of the plane, so, or the space, that are closer from 0 than from any other point in the lattice. So here I look at all the points such that the distance between this point and 0 is smaller than the distance between this point and any non-zero vector of the lattice. So here in practice, if you want to draw it, you just look at the bisectors and then you look at the intersections and you get the region. Okay, that's a very important object for a lattice. That's very nice. That's hard to understand. And what's a property? This is also a fundamental region. If I translate it, then you get also the tessellation as usual. And in particular, this tells you that the volume of this region will be also the volume of the lattice, which is not obvious if you look at it like for the first time. Okay. And how can this be useful? So just imagine you have a point in Rn, and you want to find, okay, in which region will be your point. So just imagine you understand in which translate of the Voronoi cell your point lies. What does it mean? This means actually that the closest point in the lattice from your red point will be exactly the lattice point you found. So if you're unable to, so okay, what's the meaning here? The meaning is that if you understand well enough the Voronoi cell, then you're able to find the closest lattice point of any point on the space. And also what you know is that finding the closest lattice point of a point in the space, this is very hard. So what it tells you that in general, understanding the Voronoi cell of lattice is something which is computationally hard. But sometimes, okay, there are special kinds of lattices in which you understand the Voronoi cell, and this helps you having some nice algorithms to find to solve CVP, for instance. Okay, so now let's go back to the problems I was mentioning before. So what is the lattice sphere packing problem? So this is the sphere packing problem, but just with lattices. So I assume that my packing is given by a lattice. So I assume the centers of the sphere to shape a lattice. So let's look at it the other way around, and let's fix the lattice. And what will be the highest radius I can consider? Here I don't have so much of a choice. The only thing I can do here is taking balls of radius half of the minimal length of a non-zero vector of the lattice, because here this will be the constraint. If I take a radius which is a little higher, then of course the spheres will overlap, and this is not what I want. So the best thing I can take is mu over 2, where mu is the minimum of the lattice. So if you know the minimum, then you will know the packing associated to the lattice. And what is the density? Because we're interested in the density of the lattice. So since here we partition the space into equivalent cells, so if you want to understand the global picture, it's enough to understand what's going on into one cell. So you just restrict yourself to one cell, and you want to understand what's the density occupied by the spheres in this cell. So here you have four portions of sphere, and if you glue them together, then you get one sphere. So what does it tell you? That here the density by the achieved by the packing will be exactly the volume of the ball divided by the volume of the region. But what is the volume of the region? This is the volume of the lattice. So you get volume of the ball of radius mu divided by 2 to the n, because we take half the radius, and the volume of the lattice. So if you understand the minimum of the lattice, you understand the packing density. But you, of course, one more time, this is something hard. If I give you any lattice, you have to understand the minimum. This is hard. So now let's look at the covering. So in this case, I look at the covering radius, which will be the smallest radius, such that when I have sphere of this radius, I cover the whole space. Here, as you can see, we cannot so much see it with the vectors of the lattice. We don't see really what's the relation. So what you have to look at in this case is really the Voronoi cell. If you look at the Voronoi partition now, you understand, and this is if you think about the covering radius, you understand easily that what you need to understand is really the first radius, such that the ball will cover entirely the Voronoi cell. So here the tau, the covering radius, will be, you can write it as a max mean condition. So you look over all the points of Rn, you look at the lattice point which is closest, and you want to maximize this distance. So you want to understand the furthest closest point. That's the idea. So this means just you want the radius that covers the Voronoi cell. And here the equivalent of the density. So we have the density of the packing, and here we consider the thickness of the lattice. And this will be, again, the volume of the ball. So the volume of the ball with radius covering number divided by the volume of the lattice. So here, this is something which is obviously greater than 1. And for the density, of course, we had something which was less than 1. So really, you can see that these two problems are really dual from each other. And also, yeah, just to tell you one more time that they are really dual from each other. If you want to understand the packing radius, this will be the largest R, such that the ball will be included into the Voronoi cell. And if you want the covering radius, this will be the smallest R, such that the Voronoi cell is included in the ball. Right? So that's really dual. And for instance, if you want, you can see that if you want the lattice that will be good for both, then you need a Voronoi cell that will be spherical. Look like a sphere as much as possible. Okay, and what will be the lattice kissing number? This will just be the number of minimal vectors, right? So if I just assume that the central sphere will be the sphere centered at 0, then I need to know how many spheres I can have around, and so this will be the number of, so every contact sphere will correspond to a vector of minimal length. So here I have 6, and of course they do not overlap because they are minimal vectors, right? So the distance between two of them cannot be smaller. So understanding the kissing number of lattice will be just understanding the number of minimal vectors. Okay, so this was for the part about definitions and objects. Any questions so far?
Well, Jared asked on the chat that reduced bases were, like, if reduced bases are nice examples or cases of nice bases.
I can hear you so well. I'm sorry.
Sorry. They ask on the chat if reduced bases are examples or of nice bases in general.
Yeah, you can. Okay, this is so nice basis. You don't have. It's really hard to get. Yeah. So reduced basis is kind of nice. It's something between nice and ugly, but it's in practice sometimes nice enough. Okay. Yeah, but yeah, that's what you have to think about.
So that was what we had. Please continue.
Okay, so now let me show you some examples. So what are the most famous lattices, and also how to construct lattices in general. So let's start with the very first example. We saw many pictures of it so far, but it's just a warm-up just to remember the definitions. So the lattice Zn, of course, what will be the generating matrix? So you just take the canonical basis of Rn, so identity matrix, the gram matrix. Also remember, this is the matrix of inner products. This will be also identity matrix. And then you can compute the invariance I was telling you about. The volume will be 1 because you have identity matrix, so the determinant is 1. Packing radius, the smallest vectors have norm 1, so the packing radius will be 1/2. The covering radius, here you understand the Voronoi cell. In this situation, the Voronoi cell will just be the cube with diameter 1, and so the size will be 1/2. So if you want to cover it, you need to take the diagonal, and the diagonal will be square root n. So you have square root n over 2. The kissing number, so you just have to look at the minimal vector. So you have all the vectors of the canonical basis and their opposite. So you have 1, 0, 0 and minus 1, 0, 0. So you have 2 times n vectors. And the dualis itself. Okay, so that's a very easy lattice. It's not good for many problems, but at least everything is easy to compute for it. Okay, the second lattice, which is very famous, is the lattice AN. So here, the easiest way to present it is to look in one more dimension. So you look in Z to the n plus 1. You look at all the points, so with integer coordinates, such that the coordinates sum up to 0. So you're in the so you look all the points with integer coordinates that are in the hyperplane given by the equation sum of the xi is 0. So this is also very famous example. You will see why. I will tell you afterwards why, and you will see that you know some example of it. So what will be a generating matrix? So this one, you just take the elements that are of the form ei minus ej. Gram matrix, you can compute it. You just take the product. That's not very interesting, but it's just okay. Now you have the ID card of every standard lattice. This is good to see once. And also in this situation, we know you can compute the volume. You just compute the determinant by induction. That's quite easy. Taking radius here, the norm of the smallest vector will be square root of 2. So square root of 2 divided by 2. And also, I won't go into details, but in this case, we know also the Voronoi cell, so we can compute the covering radius and the kissing number. Also, we know how many short vectors we have, and we also know the dual. So the dual will be the projection of Zn plus 1 into the hyperplane I was telling you, so into the hyperplane. So everything is also very easy, very well known for this one, but still, this one you will see that this one is already good enough for some problem in low dimensions. And the other one, the other family of lattices that is really important and well known is the lattice Dn. So here you take all the points in Zn such that the sum of the coordinates is even. So the sum of coordinates is 0 mod 2. So again, the generating matrix really looks like the one from An, but you also have the points of the form 1 1 0 0. So not only 1 minus 1 0 0, but also 1 1 0 0. You have more short vectors. So this will be generating matrix, and again, you can compute the graph matrix. The volume is also by induction quite easy to check. Packing radius will be the same because the length of the short vector will be the same. Also, you can compute the Voronoi cell in this case. That's not hard. So you get the covering radius and the kissing number. So again, understanding the number of vectors, that's easy. And the dual, this will be just made of 4 copies of the same lattices, but each of them will be translated. Okay, so this was just to tell you that, okay, there are lattices for which we know basically everything, but in general, that's not the case. But yeah, I think it's good to hear about them once in your life. Okay, now let me tell you how we can construct some lattices from codes, for instance. So I take just, so there are many ways to construct lattices from codes. I'll just show you the easiest one, which is really the most natural, and that's also a good way to see connections between linear codes and lattices. So we'll just start with Zn as usual, and you just look at the standard projection onto fp to the n. So you just quotient by p. You just look mod p. And so and you look, so now you're in fp to the n, and you look at k-dimensional code. So what is k-dimensional code? This is just a subspace of fp to the n of dimension k, linear subset of dimension k. So here in the picture, I don't have so much choice for dimensions, but I'm looking for p equals 3. So I'm looking here over these 9 points, which is f3 to the f3 squared. I'm not taking the code, so this is a line in fp squared. So I have my 3 points. This is a line, and I want to lift this code and to produce a lattice from it. So what I can do, this is very natural. I just look at the counter image over the projection. So if I look at the counter image, I get this lattice here. And you can, if you understand well the code well enough, some property, and you're careful with your code, then you can understand somehow what's going on with the associated lattice. In particular, by construction, then this will be a sublattice of Zn. And by construction, it will also contains the kernel of the map, which will be p times Zn. So you have this inclusion, and this allows you, for instance, to understand what is the volume of the lattice. This will be p times n minus the dimension. That's quite easy to understand. Okay, so this seems a bit naive, but actually you have many nice codes, nice lattices that are obtained this way. We already saw one of them. Dn, for instance. So Dn, if you look at Dn, you can just start from the code which is made of all the points in f2 to Dn. So you take just 0 1s. I just want the sum to be 0 mod 2, so 0 in f2. So this is a standard code. Here, for instance, this is just a code in dimension 3. So you just have from 0 0 0, 0 1 1, 1 0 1, 1 1 0. And when you lift it, you get Dn. So in this case, D3. And this is the face-centered cubic lattice. And you will see that this is a very famous lattice, and that's really important in applications. Okay, so this is not that naive, and you can get good codes. And actually, you have also many other codes, lattices construct that way. And one of the most famous lattices, you will see why also afterwards, is the lattice E8. You have many ways to construct E8, but one of the easiest to understand might be just by lifting the Hamming code. So you have a binary code in dimension 8, and you can lift it, and this will give you E8 basically up to scaling. So that's a fascinating lattice. You will see that this is really good for many problems. But yeah, and you have many ways to construct it. This is the easiest one. And also Leech lattice, which is also a very nice object. Also many ways to construct it, but you can also obtain it with code, with the so-called Golly code. I don't want to go into detail because this will take me some time. But just imagine that you have some very nice structures that come from very nice code. Okay. This was for codes. Oh yeah, okay, a couple more of definitions, because this is something you can hear also in the literature. So I would say that the lattice is integral if for every pair of points the inner product will be integer. So this means that the lattice is included into its dual. So remember that the dual is the set of points such that the inner product will be an integer. Even if I say that the lattice will be even if for every pair the inner product will be even. So this is actually important, but I'm not sure we'll have time to see why. Unimodular if it's equal to its dual. And we have a family of lattices which are called the root lattices. So these are integral lattices, and they are spanned by what we call roots, and roots will be elements of such that the norm squared will be 2. And this has actually some connections with Lie theory, and this has some connections with really deep algebra, and yeah, that's really interesting. I don't have time to go into this, but yeah, if you're interested in Lie groups and these kind of things, you can look at this connection. That's very nice. So for instance, one property that make them nice, but that's more the other way around, that nice lattice, such lattices are nice, that E8 and lambda 24 are, and Leech lattice are even unimodular lattices. They're not so many in nature, and people are looking for them because usually they give good packings. And also the root lattices, so that's why we know them, because we know explicit constructions, and we know that every root lattice in any dimension, you can decompose it as an orthogonal sum of irreducible root lattices. And the irreducible root lattices, we already saw them. They are AN, DN, E8 that I just mentioned, and E7 and E6 that are basically sections of E8. But this is, so E7 will be in dimension 7 and E6 will be in dimension 6, and that's it. So whenever you have a root lattice, then you understand it basically. Okay, and the last construction I want to tell you will be the construction for a number theory. So first of all, so let's go back to the definition of a lattice. So I told you you have just a discrete subgroup of Rn, and Rn with this, the standard scalar product. But actually, you could also start with a 3Z module of a given rank M. And what you need for having an Euclidean lattice, you need the scalar product. You need the Euclidean structure on the tensor product with R. Okay, so you can think of this definition now. And so now if I want to construct lattice from number theory, then first I need to construct the good Euclidean space to look at. So I start with a number field, so just number field of degree n. And okay, I have a number field of degree n, so if I tensor out by R, I will have a vector space over R of rank n also. So I want a way to go from K to this space. And actually I have natural tools to do so. I have the embeddings of the number fields into R and C. So as you know, we have n embeddings, so you can split it at R1 plus 2 times R2. So R1 will be the number of real embeddings, the embeddings of the number of fields into R. And then you have 2 times R2 embeddings into C, and you know that they come by pair, right? So you have one and the other one will be conjugate of this one. So if you want to go into this space of into Rn, so if actually you can just forget about for any pair you can just take one of the embeddings. So in this case you go into R times R1 times C times R2, and this is basically R to the n. This is what you want. So you use the embeddings, and then you get into the space you want over R, and then what you need is the scalar product in this space. So what will be the scalar product? Actually, this will be given by the trace 4. So just look at, for every pair, x, y, you look at the trace of x times the conjugate of y, where y, the bar here is the complex conjugation. And you can check that this is actually a scalar product on this space on Kr. And of course you can write it, so this will be the sum of the sigma x, sigma y bar. You can write it in terms of the embeddings, and this will give you also the standard Euclidean structure with the standard embeddings. Okay, so this is just for the Euclidean space, and now how can I construct lattices? So what is the most natural thing to look at? This is just a ring of integers, right? So if you look at the ring of integers, you know that this is a free Z modulo of rank n, where n is the degree of the number field. And then if you look at the image of so the embedding of this free module, then you get exactly a lattice, because you have a free module of rank n into the Euclidean space. That's a lattice. Actually, you can say things about it. It's not hard to convince yourself that the determinant of this lattice will be exactly the absolute value of the discriminant of the number field. This actually this comes from the definition of the discriminant, and so you understand the volume. The volume will be the square root of the absolute value of the discriminant, and you can also compute the minimum. The minimum will be square root of n. So that's actually not hard to check. That's a good exercise if you want to do it. But that's quite easy. And more generally, so this was just for the ring of integers, but if you take any fractional deal, then we'll get also this image structure, and then you get a lattice. And this is what we call, this is also what Alex mentioned yesterday, this is what we call ideal lattices, and they're really important lattices right now, currently. And also you can even generalize them, because so here I had lattices, so I thought about modules over Z, but actually ideal lattice, this you can think of it as an OK module of rank 1. And you can generalize this situation. So instead of looking at OK modules of rank 1, you can look at OK modules of higher rank, and then you will get also algebraic lattices, but with more freedom. And then this is what you call the module lattices that are also important right now. Okay, so this was all for the overview on the properties. And now I want to go back to the initial problems and tell you what are the solutions, what we know about the problems. But is there any question before?
There's nothing on the tab.
Okay. Okay, so I will mainly focus on sphere packing, and I will tell you also a few words about the other problems. So sphere packing, dimension 1, okay, if you've heard about it, that's completely trivial, because here the balls are segments and the density will be exactly 1. Dimension 2, I think you also thought of the solution. Yes, it is what you think. It's really the hexagonal lattice. So everyone knows it, like even in practice, like for instance, I saw that in the train station in Paris, that's the way they were actually organizing people waiting for the trains during this period. So they're doing it correctly. That's great. But actually, that's not so easy to prove. So this was first proven by Lagrange in 1773, that this is the best packing among lattices. So this is already a result. And then people had to prove that this you cannot do better with more general packing. So if you don't impose any structure, why couldn't you do better? Actually, you can't. So this was their first proof by Thu in 1892, but were not completely convincing to everyone. And the first convincing proof for everyone was the one by Fejestas in 1940. So this is already for dimension 2. So already for dimension 2, there was something to do that was not easy. In dimension 3, so this is also what you expect if you thought about it. This is the phase center cubic lattice. This is also in practice. This is the way you see people packing oranges in the market. And this is the lattice A3, which is also these three. Like in dimension 3, both lattices coincide. And again, this is actually a very hard result. So this was a very old conjecture by Kepler in the 17th century. And again, for proving that this was the best among the lattices, this was made by Gauss in the 19th century. But to prove that you cannot do better with any other packing, this came much later. And actually, this came very recently, because this is due to Thomas Hales, who first gave a proof in 1998, which was not so convincing, because so what he did basically, that everything boils down to a finite number of configurations to check, but there is really a huge number of configurations to check. So people were not completely convinced that everything was correct. But actually, then with a huge number of co-authors, they provided proof in 2014, which is made of, which is supported by computer assistants, like to make sure that really everything that you should check is indeed checked and is indeed correct. So the full proof is just 6 years ago. Okay, so what do we know more, after this? So until dimension 8 and also in dimension 24, we know the best lattice. So we know the best packing among the lattice packings, but really just among the lattices. And you can see that this is the ones I presented you before. So in dimension 4 and 5, they are given by D4 and D5. And then 6, 7, 8 by the root lattices E6, E7, E8. In dimension 24 by the Leech lattice. So this one, we know that they are the best lattices. And even more surprisingly, what we know in dimension 8 and 24, that the candidates, E8 and the Leech lattice, they actually give the best packing. And people could prove that this is optimal, and also this is the unique optimal solution. And this is very recent. This is due to Marina Wierzowska, like 4 years ago. Which is surprising, because dimension 4 already we cannot prove it, but dimension 8 and 24, this is completely understood. Okay, now what about in higher dimension? So we have an upper bound, so we know that the density will. So this is the bound for the density, yeah. So we know that the density decreases exponentially, and so we have a bound which is quite old actually. So you have some slight improvements, but basically that's what people know. And for lower bound, so there has been a bit more progress, but you will see that not so much. So the first result in this favor will be the result by Minkowski-Lawka, which tells you that the density will be at least 2 over 2 to the n. So you will see that we have a huge gap in the exponent. So here this is also exponential, but here we have a -1, and here we have -1/2 almost. So what people could expect is then improving here the exponent in front of the n, but actually the only improvement were on the numerators. So first here we have a constant on the numerator, and then the first bunch of improvements were made on the numerator to provide linear improvement in the numerator. So first Rogers, and then people improved the constant in front of it, but basically the constant was not more than 2. And then in 2013, then Venkatesh came up with a paper that was important for this field. Like it could improve the constant, like importantly for all dimensions, and most importantly, it could prove that we have more than the linear growth of the numerator. It could have this additional log n factor. And the problem with all these things that, okay, yeah, you know that such lattices exist. So this is for lattices. So you know that in theory they exist, because you do some average argument on random families of lattices, but you don't know how to construct them. If you want an algorithm to do so, you don't have many things. Still, you have some exponential algorithm, but they cannot run because like they're really huge. Like, just to give you an idea, solving SVP is cost less than enumerating the families. So in theory, we have algorithm, but they're really fine for using them in practice. But still, this is a bit more effective than what's supposed. So you have this result by Rush, which gives essentially the bound by Minkowski-Lawka. Then you have a result by Gabor and Zemmour, which recovers the linear factor. And then during my PhD thesis, I have the equivalent of the result by Venkatesh. So, but here also using finite families. So with kind of an algorithm. Okay, I don't know if I have time, I can tell you about the proof. Maybe not. Okay. So let me skip this. I will tell you. So this is just, okay, how you can prove that then the bound is at most 1 over n, and then how we can use lattices to do more. But I don't have time to go into it. I don't want to run over time. Okay, I want to tell you a bit what we know about the kissing number, for instance. So dimension 1 and 2, we already saw it. That's basically trivial. Dimension 3, so this was also a big story. So there is this fight, which is well known between Newton and Grigori. Like Newton was saying that, so here we have a configuration with 12 balls. So the 4 here that you can see, and you have 4 behind that are disposed in the same way. So you have 12 spheres. And what you can see here that you have actually a lot of space between spheres. So actually you can even move them and you have really a lot of space. So you can even continuously move the balls, still touching the central ball, and then you can swap two of the balls. So you have definitely, you have a lot of space. And that's why Grigori, for instance, felt that you could add one more sphere into this configuration at some place. But actually, it's not true. So 12 is really optimal, and this was proved by Schitte and van der Waarden, and this is quite recent also. This is just in 1953. These were really old problems, but solutions came late. In dimension 4, so here, for instance, in dimension 3, so this is highly non-unique because you can move the balls. In dimension 4, we know that the solution is 24. This is given by the lattice D4, but it's also conjectured to be unique but not proven. And that's all the cases we know, except, of course, as you can imagine now, dimension 8, when we know the solution, and then dimension 24. And as you can guess, the solutions are given by E8 and by the Leech lattice, and they're also known to be unique. So this is just to give you an intuition how special are these configurations, E8 and the Leech lattice, because they solve their problem in their dimensions, like for almost every problem. Okay, and what if I look asymptotically again? So we have an upper bound, which is actually comes from the same paper for the sphere packing. You have the bound for the Kissing number. So we have also that we know that we have an exponential bound. So the exponent will be 0, 40, 41. Now, if you look at random packing, so not looking at the lattice Kissing number, but Kissing number in general, then you know also that you have an exponential increase. You know that you can construct things, but okay, you don't know how to construct it, but you know you can do it. This is by some random arguments. And for lattices, this was not clear actually, that you had some exponential growth. But now recently, like last year, Vladit showed that, yeah, you do have lattices with exponentially large Kissing numbers. And these lattices are constructed with codes, and codes from algebraic geometry, GOPA codes for people who know what they are. That's actually a very nice paper. This was, so people were not expecting this kind of construction, but actually, yeah, you can prove that. But still, and the exponent is slower than this one. So you have construction, but the exponent is smaller. But still, you have exponential increase with lattices. And just to conclude with coverings. This is even harder. Actually, this is the problem we know even less about. So dimension 1, we know the solution. That's again trivial. And dimension 2, we know the solution. This is again given by the hexagonal lattice A2, so which is good for every problem. And then we just know the best lattice covering in dimension 3, 4, and 5, which is given by the dual lattice of AN. So actually, you might expect that this will be the case afterwards, but it's already known that in dimension 6, this is not optimal. And then it's also all what we know. Asymptotically, the best bound, and people cannot improve it, is the one by Rogers, which is from the 60s. So we know that the densities, the lattice covering, the thickness will be at most n log n to the c. And if you look at the lattices, so you have some bound also, but oh, sorry. So this was for lattices, but this is not as good as for general coverings. If you look at general coverings, then you have n log n, which is better. But so for these two problems, actually, lattices in the low dimension, they are useful because all the solutions are given by lattices. But if you look in high dimensions, then it's not so clear that they are good. But still, for a sphere packing, then the best solutions we know in high dimensions come from lattices. Okay, and then I will stop here. I think, yeah.